Okay,
What if I told you that typing a few specific words into a prompt can change the actual mathematical class of problems an AI is capable of solving? Not seems smarter, provably, mathematically capable of more.
sounds totally like science fiction, right? Well, in this explainer, we're unpacking a groundbreaking paper from researchers at Stanford and Google that uncovers exactly why this happens. We're going to see how a tiny shift in how we talk to AI completely redefines what it can actually solve. And those magic words? Let's think step by step, or as the researchers officially call it, chain of thought prompting. Now look, we've known for a while that asking a large language model to show its work makes it seem smarter, but this paper proves that
Mathematically, that this isn't a vibe. It changes the literal computational class of problems a transformer can solve. So why does this one change matter so much? Why does letting a model think out loud unlock problems it otherwise can't touch, no matter how big you scale it? To understand where AI reasoning is actually headed, we need to get into the real mathematical mechanism behind this prompt.
because you see, there's a massive catch to how AI naturally thinks, which we'll get to in just a second. Part 1. Standard transformers hit a wall. To really get this breakthrough, we first need to look at the critical limitation of standard AI models that Stanford and Google were trying to solve here. Think of it kind of like this. Standard AI is like an incredibly fast reader who tries to read an entire 500-page book in a single second. Thanks to parallel computing, it basically scans all the words at once, which is, incredibly efficient. But if you ask it a deep, logical question that requires connecting a tiny clue on page 10 to a major plot twist on page 400, it completely fails. It lacks that deep logic. Serial computing, on the other hand, is like reading page by page, taking notes, and building a conclusion step by step.
A vanilla transformer, left to answer in one shot, is bad at this by construction. This is what the paper formalizes as a hard architectural limit. Without chain of thought, a transformer's ability to do sequential computation is capped by its depth, its fixed number of internal layers. Once information passes through those layers, it has to output an answer. That hard caps how much serial reasoning it can do in a single pass. It hits a wall on genuinely multi-step logic. Enter chain of thought, or COT. The researchers show it rescues the model from exactly this constraint by letting the model generate intermediate tokens, essentially thinking out loud before finalizing an answer. It gains the ability to perform computation that's inherently serial, step building on step, instead of everything happening in one flattened pass. Part 2. How chain of thought actually works. Now, one honest note before we dig in. What you're about to see isn't someone typing into ChatGPT and watching it improve. This is the paper's own controlled setup. Small transformers trained from scratch on synthetic math and logic tasks, specifically built to isolate this one mechanism cleanly. That's what makes the proof rigorous.
The researchers use a concept called circuit complexity. Imagine measuring the AI's brain power by mapping its thoughts to a theoretical network of basic logical gates, kind of like the simple and, or, and not gates inside your computer chip. To know how smart a model is, we just look at the size and the depth of the logical circuit it can successfully simulate. The researchers literally prove that each single step in a chain of thought simulates exactly one logical gate operation. Mathematically, the AI maps out the circuit in real time, with each generated word acting as a brand new gate, feeding perfectly into the next one. Okay, let's layer in the actual technical terminology so we really grasp the magnitude of this. Vanilla AI,
or vanilla transformer,
is what we call constant depth. It's trapped in these restrictive
complexity classes called AC0 or TC0. This part is unconditionally proven, which makes certain serial logic mathematically out of reach, not just difficult. But with chain of thought, the model can reach a vastly larger complexity class called p-poly, able to solve any problem expressible as a polynomial-size logical circuit. It's the difference between a calculator and something closer to a general-purpose compute. How does it get there? By auto-regressively generating tokens, writing a step down, then feeding that step back in as new input. Every time it writes a token, its effective computational depth resets. It's buying itself more processing depth than its fixed architecture would otherwise allow, sidestepping the hardware limit rather than breaking it.
Part 3. The real-world AI payoff. Okay, we've talked a lot about the theoretical math, but let's pivot to the empirical proof to see how this fundamentally changes the game. Just check out these heat maps for a really complex math task called permutation composition.
A task that's provably hard to parallelize. Without COT, accuracy sits around 20%, which is basically random guessing among 5 options. With COT, the same model jumps dramatically. the paper reports the improvement as consistently huge, especially for shallow models. The gap between those two conditions is the clearest empirical signature of the theory holding up. Then there's iterated squaring, a deeply sequential math problem. Same story. Standard models without COT struggle badly. With chain of thought, the paper reports this task can be solved essentially perfectly, even by a model with just one layer of depth. Worth being precise here. The architectural upper bounds are unconditionally proven math. The claim that these specific tasks truly require serial computation rests on standard, widely believed, but still technically unproven, complexity theory conjectures. That's normal for this field, and it doesn't weaken the result. It's just the honest framing. So what's the takeaway? If this generalizes the way the theory suggests, prompting a model to reason step by step isn't a cosmetic trick. Here's where I'll flag my own extrapolation rather than the paper's claim. If this holds at scale, it points toward coding agents handling genuinely sequential logic they currently choke on, and multi-step robotic planning that doesn't just freeze on complex chains. What the paper does support directly. Prompt design isn't just a nice-to-have. It's mathematically load-bearing. And it suggests smaller models with the right prompting could reach capability classes that raw scale alone wouldn't get them to. The core proof here is that adding intermediate steps mathematically moves a transformer into a different class of computing power, not just a different vibe, which raises the real question. If a simple prompt today changes what's mathematically reachable, what happens with architectures explicitly designed to reason in longer, self-correcting loops? Let's debate that in the comments. Thanks for joining me on this one. Keep learning.